Alright, here's a first tutorial regarding the time series modeling. So, time series modeling is one of the most popular forecasting model used widely in different industries. Today, we're gonna dive into the time series modeling and time series data. Here is the outline of this tutorial. First, I will spend some time talking about the definition and application of time series data and time series modeling. And I will also cover the time series features. Some important feature includes trend, seasonality, white noise. Stationarity is actually another important characteristic for any time series data. I will talk about how to do the stationarity check and how to remove the non-stationarity part from the time series data. Most importantly, I will spend time talking about different algorithms used to build the time series model. For example, the autoregressive, moving average, ARMA, and Arima model. Lastly, I will also implement the time series model using Python and Jupyter Notebook to build a Arima model to forecast the value of the future value of a time series data. The second way is I will use Tableau to implement a time series model and also forecast the future value of time series data. So the second way is a little bit different than the first way. Tableau is a popular business intelligence software used among different industries. And by using Tableau, we don't actually need to do any programming. We can just now let's go ahead and understand the time series modeling in detail. So time series model are useful model when you have serially correlated data. For example, on the right hand side, we have a plot of sales of monthly series of monthly sale data. And from this plot, we can see the only independent variable on the x-axis is the time step, and the y-axis as the dependent variable is the monthly sale data. So we can actually conclude that the time series can be defined as a set of measurements of certain variable made at a regular time intervals, and time acts as an independent variable for the estimation. For any time series model, the time is the only independent variable for the model. And a time series defined by the values of y1, y2 of variable y at different times, like t1, t2, t3, is given by this function. Y is equal to the function of t, and t is the time, which is the only independent variable for any time series models. And y is the time series value correspond to different time steps. Okay. Time series forecasting is the use of a model to predict the future value based on the previously observed value. And time series modeling can be applied to any dataset that include the time, such as the daily stock price and the daily sales of e-commerce, and the monthly tickets sold by an airline, and monthly production of shoe manufacturing company. And there's one thing to be noticed is that all the datasets have to include the time component to be counted as a time series data. Okay, now let's talk about the time series features. As I mentioned before, the time series has several key features such as trend, seasonality, and noise. Let's look at the trend first. So a trend is a long-term increase or decrease in time series data, and the trend can either be uptrend and downtrend. Let's look at the first plot. It's uptrend. So as we can see, this time series data started from somewhere around like 200, and it ended up at the 600. So in the process, anything in between may maybe zigzagging, but generally speaking, this time series is trending upward. It's increasing. It's increasing as the time increase. So this is uptrend, and similar thing for the downtrend. And seasonality. So seasonal pattern exists when a series is dependent on the seasonal factors such as the day of week, month, or quarter of the year. And seasonality is always of a fixed and known frequency. For example, from this plot, we can easily find out that the time series reaches the peak from the bottom every around like 3 years. It's kind of periodical, so we can conclude this time series data has strong seasonality. And leveraging this seasonality, we can actually make a time series model more accurate. The white noise. The white noise is lots of things you want from your time series data. So basically, white noise theory is just one with zero means and constant variance, and no correlation between its value at different times, which means that, for example, on this point, so this point is totally non-correlated with any other points on the plot. So, which means if your data is white noise data, you can actually not build any practical model using that data, and you cannot make any predictions. It's unpredictable. Let's now understand what is stationarity. Stationarity is an important characteristic of time series. If the statistical property of time series do not change over time, then we can say the time series data is said to be stationary. In other words, it has constant mean, variance, and covariance, and all those three statistical properties are independent of the time. So let's look at the plot. It's clearly that we can see this time series data has constant mean around 15, and the variance is also constant. They're all those statistical properties are independent of the time, so we can conclude this time series data is stationary series. Basically, there are two methods which we can use to do the stationarity check. The first one is called rolling statistic. So basically, from the graph, we see the blue line is the original time series data. We want to check whether this time series data is stationary or not. We apply the rolling mean and rolling standard deviation on the original data. We got the red line as the rolling mean and green line as the rolling standard deviation. It's apparent that the rolling mean has the uptrend, same as the rolling standard deviation. They're not constant, and they kind of are dependent to the time. So this time series data is not stationary. And the other way is we can apply the Dickey-Fuller test, which is a statistical hypothesis test. So we set non-hypothesis as time series data is non-stationary, and if the test statistic is less than the critical value, we just reject the non-hypothesis. In this case, if we reject the non-hypothesis, that means the time series data is stationary. So actually, in the most of case, it's impossible to get a time series data to be perfectly stationary. So we are targeting to get a data as stationary as possible by using several different approaches. So differencing is one of the approaches that is the most convenient but equally powerful. So differencing is performed by subtracting the previous observations from the current observations. And here is the equation. Basically, the delta is the difference between two successive values, and the yt is the value of the y at the t, and the yt minus 1 is the values preceding yt. So, for example, here is the time series data before applying the differencing. So as we can see, this one is non-stationary series. After applying differencing technique, we got almost stationary data set. So we can build up a time series model using this processed time series data. All right, let's see the different algorithms for the time series modeling. So autoregressive AR models predict the future behaviors based on the past values, and it is used for forecasting when there's correlation between values in time series and the values that precede and succeed them. So the process basically is a linear regression of the data in the current time series against one or more past values in the same series. So the equation for autoregressive model is listed as follows. The y is the function of the different past value of the same variable, and et is just error term, and c is constant. Psi1 to psi p are the parameters. So basically what this means is, for example, you want to forecast the value of yt at the day 12. So basically you assume that this yt is somehow correlated with the values before it, like the value is correlated correlated with the value that in the past, like 10, 11, 10 day all the way to the first day. So, and also this p is the cutoff time point. Then this p is everything before p, we don't need to consider that. The p is the parameter we need to determine for this AR model. And AR1 is the model whose current value is based on the preceding value. Basically, this means the p-value is 1. So, for example, if I want to predict yt, we only need to consider yt minus 1. And AR2 is based on preceding two values. Figure out yt, we need to consider yt1 and yt minus 1 and yt minus 2. A moving average model uses the past forecast errors in regression-like model rather than using the past values of forecast variable in regression as seen here. So mu is the mean of the series, and psi1 to psi p are the parameters we need to figure it out. And et is the error term. The error term here are assumed to be the white noise processes with mean 0 and constant variance. The ARMA model is simply the merge between AR and MA models. So the ARMA model attempts to capture both those aspects when modeling the time series models. So in this way, it's more powerful. It can easily detect the any hidden patterns among the time series models. And for this ARMA model, there are two parameters we need to figure out, we need to determine before running the model, which P is from the auto regression part, and Q is from the moving average part. So Arima model predicts the value in the response time series as a linear combination of its own past values, past errors, and also current and past values of other time series. So similar thing, but this Arima model, comparing with the ARMA model, it has the D term. D is the order of differencing. Basically, this model also take care of the stationarity part. It automatically will remove the non-stationarity part from the time series data by passing the D, which is the order of the differencing. So now let's look at the autocorrelation ACF and PCF. So ACF is autocorrelation function, and PACF is partial autocorrelation function. So as I mentioned before, in order to build a Arima or ARMA model, we need to figure out two most important parameters, which are P and Q, from autoregression part and the moving average part, respectively. F is coefficient of correlation between value of a point at a current time and its values at like P. That is correlation between the YT and YT minus P. So by analyzing the ACF, we can determine the order of MA process, which we can determine the value of Q. Similar thing for the PACF. So PACF is similar to ACF, but the intermediate lags between T and T minus P are removed. That is correlation between YT and YTP with P minus 1 lags excluded. So PACF will be used to determine the order of AC process, which we can get the value of P. So here's the characteristic of those two functions, ACF and PACF. So here's some rules to help us to determine the value of P and value of Q. So I'm not gonna just keep. So here are some rules can help us to determine the value of P and the value of Q from the graph. So basically, we can use those two functions to plot the ACF graph and PACF graph. And following those rules, we can find out the value of P and the value of Q, and then plug those two parameters into the Arima model, and then train the model use the time series data. So the steps in time series forecasting. The first step is always visualize the time series data, check for trend, seasonality, random patterns. And also in the second step, we need to stationarize the series using decomposition and differencing technologies, and plot ACF and PACF, find out the three most important parameters for Arima model if we use Arima to forecast the time series data. So P, D, Q, three parameters, and build Arima model and make prediction using the final Arima model. Okay, now let's look at the demonstration of how to build a time series model using Arima technique. So the dataset I found is regarding the industry production of electric and gas utilities from the year of 1931 to 2021. So the first step is we're going to include the relevant libraries from Python. So these two libraries are most important for this project. And this seasonal decompose is the function I'm going to use to decompose time series data to find out is there any trend or is there any stationarities. And auto Arima is a Riemann function which is going to build a model for us. This one has one benefit comparing with traditional Arima model. This is called auto Arima. That means we don't have to manually figure out which P and which Q value fits the model best. We can just set a lower bound and higher bound for the P and Q value, and this algorithm can automatically try different combinations and give us the most suitable combination of P and D, P, Q, and D values for us to build the Arima model. So with the library being loaded, let's load the data. Check the data here. Just data. So here's our data. We have 989 rows and we just have two variables. One's the date, another is actual. So I'm gonna do a little bit data wrangling here. What I will do is I will set the date to the date-time format, and also set the date as the index of the time series data frame. So here is the result after the data wrangling. As we see, the date has become the index of this entire data frame, and I only have one column which is called actual. Is the actual utilities of the gas, electric at different months of different years. We have from 1939 to 2021. And we can visualize that time series data and also decompose that using the seasonal decomposition. Here's the decomposition plot. The first plot is just original data. Currently, we can see the uptrend pattern is increasingly across the years. And here is the trend. It's uptrend. And here is the seasonal plot. You can see this actually is changing periodically. It definitely has a seasonal, it has strong seasonalities. We don't need to worry about the last plot too much. And with that being found, we can now stationalize a series, find out the PDQ parameters using the auto Arima model. I have date as my input, and I also provide a starting point of the p-value as well as the starting point of the q-value, and the maximum p-value and the maximum q-value. And also this for the seasonality part, since we know this time series data has yearly seasonality, and starting p and seasonality is true, and d is the differencing part. Since we found this one has a uptrend, so it's not stationary originally. So, but this trend is not obvious. It's pretty smooth. So we only do the differencing one time. So we put d up. We put d as 1, and keep other attributes as default. And you see the program is trying different combinations for us. The value of AIC is used to evaluate how accurate of this time series model is. So basically, we want this value as low as possible. So this auto Arima model automatically found the best combination for us. P, D, Q are ones. When the PDQ values are ones, we got the lowest AIC value. We got the best. We got the most accurate model. So after that, we can split the data to training and testing side. I took the data from 1985 to 2017 as my training data, and the 2018 as until now, from 2018 until now, are my testing data. So, and this is my model. Automatically, this auto Arima automatically save the best model into this stepwise model. So select fate using the training. So I got my model now. So right now I can make the prediction. So I want to predict from 2017 December to the next 37 months, and we call the result as future forecast. And here is the prediction values. The next thing I want to change this array to the Panda data frame, and I call this prediction. and I combine this forecast with the training data. So as we can see, the line in orange are the prediction, and the line in blue are the actual data. If we want to zoom a little bit, we can just see we just compare the training data with the predicted data with the testing data. So here's the plot. We can see the line in orange is the prediction, and the blue line is actual. So as we can see, it's predict the value pretty well. Okay, now let's see another demonstration for the time series model using Tableau. So as I mentioned previously, Tableau is a business intelligence software, which is mainly used for the business intelligence reporting or dashboard designing. It's not specific used for the programming machine learning stuff. However, it does cover some simple data analytics and time series modeling forecasting kind of tools functionalities, which is really convenient since using the Tableau you don't have to code at all, so that is more friendly for the people that don't have too much coding background. So the first step we're going to do, we're going to import the data set. So that's my data set. And here is as we can see here, the previous data set is monthly data and the utilities of the gas and the electric. Let's open it, dash it. Let's put the date here, and let's put the actual here. We can just drag and drop doing every single things. Oh, oops. So we want to drill down to months, and here's the sum of actual. Here we have just visualized the entire data set, so from 0 to 0, and we can click the analytic tab. We do focus. We drag the forecasting here, and job is there. So you can see automatically. Actually, we can change the colors, make it right, more apparent. So as we can see, automatically the Tableau did some forecasting for us. So basically, it's focused. I think it's 1 year in advance. It's forecasting the utility within the 2021. We can change some parameters here. Actually, the Tableau treats the algorithm as a black box. We actually don't know which algorithm the Tableau used for the time series model. We can just consume the end result, the end model. So here's some parameter we can play around. That thing is the forecast length. So I want to forecast like 2 years, but I want to, since we only have the data until the 2021 January. So if we want to forecast 2 years with the testing data, we have to train the model using the data up to 2 years ago, which was 2018. So we're gonna ignore the last 24 months of data, so that we have the 2 years prediction up to today. So as forecast modeling, you can choose whether to turn on the seasonality or not. And you can also customize if you want the trend to be active and multi-plicit. And you can also customize the trend, the season. You can play around with that to see what the result. So here just do the automatic, since it definitely has the seasonalities here. So let's just click OK. See, here's the result of the forecasting of 2 years. If we want to zoom in a little bit, we can do the data. date, years. So we can see the results over there. And also, if we want to compare this with the actual data, which I'm going to demonstrate how to do that. So the date lectures. We need to copy paste data from this datasheet and open a new datasheet and paste all the data points here. So let's see, we have the estimate, we have the lower bound and upper bound, which are the confidence interval. So we don't need those confidence interval over there. We just need the estimate data and actual data. So I'm gonna rename it as forecast. Rename forecast, and the time is called date, and that should be the date format. Yeah, everything looks okay. And if we open another datasheet, we can put date here. Actually, it's there. Forecast, actual, and we need the monthly data, and we can do the dual access. In this way, we have those overlapped. We have those things overlapped, and we want to zoom in a little bit. We can just years. We can just check the recent years. Okay, I think that should be good enough. Okay, as we can see over there, the blue line is the actual data. The line in orange is the forecasting data. It's from the graph we see actually this model is performing pretty good.